In this linear structure of glucose, also known as the Fischer projection, the hydroxyl group of carbon number 5 will react with the aldehyde group of carbon number 1 to form an intramolecular cyclic hemiacetal. What is a hemiacetal? A hemiacetal is a compound formed when an alcohol reacts with an aldehyde. So if I just show you how this reaction takes place, here we have the aldehyde, and if this aldehyde reacts with an alcohol, what happens here is that this hydrogen ion will be given off to this oxygen, and this double bond here, one of those bonds, will now be taken up by this hydrogen ion, and a hemiacetal is formed. So you have RC single bond to a hydroxyl group now to this edge, and then OR1. So this is a hemiacetal compound, and this particular carbon now has become anomeric because it has become highly oxidized due to it being attached to two oxygen atoms, one oxygen atom here and the other oxygen atom here. So similarly, when an intramolecular cyclic hemiacetal is formed within this linear chain or open chain structure of glucose, what will happen? The glucose will undergo the process of cyclization and changes from a linear structure into a ring structure. I can simply rotate this to the right by 90 degrees, and I can draw it like this as well. Okay, here you have the first carbon atom, second, third, fourth, fifth and sixth carbon atom attached to two hydrogen molecules and one hydroxyl group. So this is CH2OH. This carbon number 1 will have the aldehyde group, okay, and the hydroxyl group of carbon number 5 will react with the aldehyde group of carbon number 1. I can also draw this structure as that, okay, when I bend some of those bonds between C1 and C2, C3 and C4, C4 and C5, okay, so we get this structure here that you can see. So here's the aldehyde group, this is carbon number 5 and this is carbon number 6, CH2OH. So what will happen here? The next step is there will be a rotation in this particular bond here, okay, so there will be a rotation of this bond that is between carbon number 5 and carbon number 4, and the rotation of this bond will then bring the hydroxyl group of carbon number 5 in close proximity to the aldehyde group. So if you can visualize this rotation here, or rather I'll just show you this using a very simple animation. So this rotation of the bond between carbon number 4 and carbon number 5 will bring the hydroxyl group of carbon number 5 closer to the aldehyde group of carbon number 1. So now we have the hydroxyl group of carbon number 5 placed very close to the aldehyde group. And now what happens here? The hydroxyl group will now attack the oxygen atom of carbon number 1, and it will react with this aldehyde group to form that cyclic hemiacetal within this structure of glucose. And now the hydroxyl group of carbon number 5 will react with the aldehyde group at one side to form alpha D glucopyranose, or will react on the other side to form beta D glucopyranose. It will become alpha D glucopyranose when the hydroxyl group formed after the reaction will be placed on the opposite side of CH2OH. And if that hydroxyl group that is now formed will come to lie on the same side as that as CH2OH, then it will be beta. So that is the main difference between alpha and beta D glucopyranose. So again, if it is lying on the opposite side of CH2OH, it will be alpha, and if it is on the same side as CH2OH, then it will be beta. The ring structure of glucose is so called because this 6-sided structure resembles pyran, which is a heterocyclic compound composed of 6 sides: 1, 2, 3, 4, 5, 6. Hence the name glucopyranose. Alpha signifies the position of hydroxyl group of carbon number 1. D means it is the dextro-rotatory form, which is the more predominant form of glucose, and pyranose to signify that it resembles pyran, and it is a sugar. It is a monosaccharide. These 3 lines here are thickened. Why? This is to show that this plane of symmetry here will be in front, and these other sides of the pyran ring are behind. So in a way, this structure that we have drawn, that you will be drawing in your paper, when you thicken this line like this, it means that the plane of symmetry of the structure of glucose should be perpendicular to the paper that you're drawing this structure on, or to whatever it is drawn at. So in this picture here, we can see that this thickened line here of these 3 sides of the pyran ring is perpendicular to this background here. So what we're trying to actually see here is this, right? We are seeing this actual plane of symmetry, okay, like that, just like that. So the 3 sides are behind and these 3 sides are in front. So that thickened line in the diagram that we have drawn, or that you'll be drawing, that is to show that those 3 sides of the pyran ring are in front. Here we can take a look at the 3D structure of glucose. This is the open chain form. This is carbon number 1, 2, 3, 4, 5. Carbon number 6. Carbon number 6 is obviously attached to 2 hydrogen atoms and 1 hydroxyl group. Okay. Carbon number 1 here is attached to 1 oxygen atom and 1 hydrogen atom. So when the cyclization occurs, what will happen? This hydroxyl group of carbon number 5 will now react with carbon number 1, and this oxygen will also be attached to carbon number 1, and this particular carbon number 1 will become anomeric, okay, and form this ring structure of glucose, or Haworth's projection. Here you have the anomeric carbon atom, which is carbon number 1, which is attached to oxygen of this particular hydroxyl group, and this solo oxygen atom here. This will be carbon number 6, and this is carbon number 5. Okay, so if I will just slightly rotate this like that, okay, so this is actually what we are supposed, or rather how we are supposed to see the ring structure of glucose. If you like this video, please hit the like button, and again, don't forget to subscribe. Thank you.